Hello dear children. The next topic in magnetic effects of current will be Ampere's circuital law. We can call this law to be ACL also as a short form. This is a law which eases you up to find out the value of magnetic field at any point due to a current carrying conductor. So, what is Ampere's circuital law? Let's have a look. The line integral of the magnetic field B vector around any closed path in the free space. Line integral means you would have to do an integration and it was over a closed path. That's why we have placed a circle here. Is equal to the mu naught times, mu naught we all know, absolute permeability of free space. Mu naught times the current passing through the surface enclosed by the closed loop. We can also say it is equal to mu naught times the current that is threading through the particular loop. So, what are the sign conventions that we use to take in this law? Sign convention number 1, you will use the right hand rule, right? Then fingers curl. While doing the question, the curl of your finger will tell you the traversing boundary of the Amperian loop. Because it is a circuital law, it is a law which is applied on some boundary, on some closed path, closed loop. So, in what direction you are going to traverse the loop will be decided by the curl of your fingers. And secondly, the thumb of the right hand will decide the direction of the current, right? And this will turn out to be the positive current. If you have to take the current in opposite direction, then fingers curl will be vice versa. So what does this law actually explain? B dot dl, what do we mean by B dot dl? You can see if on any kind of loop, if B is constant, it can be taken outside the integration. Then integration of dl will be taken. Dl meaning the closed path. Now from the previous discussion, we all know if there is a current carrying loop, let this be a straight loop carrying current, then using the right hand thumb rule, suppose this wire is kept in your right hand and thumb is in the direction of current, then the curl of your finger will tell you the direction of magnetic field. As we were discussing here, the same thing we can discuss here also. So the magnetic field is coming out from here and going in from here, meaning the magnetic field will form small concentric circles around this loop. Now we very well know these circles convey us, what does they convey? Current, the direction of magnetic field is coming out from there and going in there. So coming out, it can be represented by dot, and going in can be represented by cross. So we can get some kind of idea of the magnetic field from here. But these circular lines are also telling us the direction of the magnetic field lines. So direction is coming out from here and going in from here. Similarly for these points also. Now discussing the topic further, if we are taking B dot dl, that means we are taking the product of magnetic field with the curl, with the closed loop. If this is the circle, then dl will integrate to 2 pi r, and 2 pi r meaning the circumference of the circle. They are saying it is directly proportional to current. So what do we mean by this? If current in the wire remains constant, mu naught, if the medium remains constant, that means if this is a constant quantity, then the product of B and dl rather, should be a constant quantity, because if we know the current is constant, mu naught is constant, this product should be a constant quantity such that B and dl are inversely proportional to each other. I can write it circumference of the loop. Circumference. This is true as long as the magnetic field is in the circular path. So magnetic field and circumference are inversely proportional. See, circumference of this innermost loop is small, so its magnetic field should be larger. Of this loop is somewhat more, circumference is more, magnetic field should be lesser. Circumference more, magnetic field should be further lesser. That means while going away from a current carrying wire, the magnetic field reduces. So this is the basic idea of the Ampere circuital law. Now quickly discussing the loop that we have to take, because it is a law, so we have to apply it on different figures. So we firstly we would choose the Amperian loop, or we'll call it the loop just. So how should be the choice of Amperian loop be? So while applying it in the applications, Ampere loops should be, number one, should be chosen such as magnetic field is tangential to the loop. Mostly we take this case. Mostly in our applications we take this case. Or they say magnetic field can be a non-zero constant there. Obviously you can apply it at any point where magnetic field vanishes, or you can apply it at any point where magnetic field has a constant value. But there is nowhere written that magnetic field can have a variable value and you can choose the Amperian loop to be there. This is not the case. Point 2, magnetic field is normal to the loop. So considering these points, we are just going to the first application of the Ampere circuital law. So coming to the first application, it is called as the magnetic field due to an infinite long straight current carrying conductor. Now I have earlier told you that from the CBSE syllabus there were two points where we used to find out the magnetic field due to a straight wire. One was with the help of Biot-Savart's law. One was with the help of Biot-Savart's law, and second with ACL, that is Ampere circuital law. Now this is not in the syllabus anymore, so we'll be doing it using Ampere circuital law. So if it comes in your exam, you also are going to write it using Ampere circuital law. So what should we do? First of all, consider a long straight current carrying conductor. Magnetic field is produced due to the current flowing in the conductor. Suppose this is the current carrying conductor. Why am I writing it like, why I am drawing it like dotted lines? Because it is infinite. We don't know where the corners of the wire are. So that's why we should draw it in the infinite manner. So firstly, current flowing is upwards. Apply the conventional rule. Conventional rule says, first of all, thumb should be in the direction of current. Fingers curl, fingers jadar curl hongi, that should be the direction of Amperian loops traversing. Amperian loop we must select. First of all, let this be point P. This is point of interest. Distance of point P from the current carrying wire is, let's say this distance is equal to R. So at the point of interest we are going to draw an Amperian loop. Now at this Amperian loop, the traversing direction is in anti-clockwise direction, because we have seen the curl of the finger was in anti-clockwise direction. So where should be the magnetic field? Number one, tangent to this point. This is the magnetic field. And where should be the dl vector? Because we are traversing in anti-clockwise direction. So at any point, displacement vector dl will be kind of tangent. So now applying Ampere circuital law. So apply Ampere circuital law. B vector dot dl vector is equal to mu naught times the current. Now working on the left hand side, first of all, integration we people are doing. Now as at this point we have, suppose the magnetic field, suppose it's a constant quantity, so magnetic field dl dot product, meaning cos of angle between them, both are in the same direction, that's why cos 0 degree. Integration, then working on this only, magnetic field is constant, can be taken outside, then integration of dl, because cos 0 is equal to 1. Now how will we integrate dl? Dl meaning small portion of this loop, integration meaning complete loop, length of the complete loop meaning circumference 2 pi r, and this should equate to mu naught times I. So what should be the value of magnetic field using this equation? Mu naught times I over 2 pi into r. So this is the value of magnetic field at any distance r from a straight wire carrying current. Now we can change this formula into somewhat we know and we used to write. So that is, we used to write mu naught upon 4 pi. So multiply by 2 and divide by 2. It will be mu naught upon 4 pi 2I over r. Because we can put down the value of mu naught upon 4 pi to be 10 to the power minus 7 while doing the numerical. You can use or learn this formula or this formula, both are equal. So from here it is clear that magnetic field due to a straight current carrying conductor is inversely proportional to the distance. Inversely proportional to distance. That means while we are moving away from the current carrying wire, that means r increases, the magnetic field will decrease in accordance with. So from this formula, we can study this formula first of all. From this formula, number one, it is clear that the magnetic field of a straight current carrying conductor is cylindrically symmetric. Cylindrically symmetric. Why so? Because symmetric. Because at a distance r, value of magnetic field will be same. Distance taken from here will be same. So if we'll draw a cylinder about this current carrying wire, that cylinder will possess a value of magnetic field will be same at every point. Second point is, these circular lines which are drawn around this are called the magnetic lines of force. So we can draw the magnetic lines of force about this also. Third point that we shall discuss from here, that it is in accordance with Oersted's experiment. We did at the first of this chapter, we did Oersted's experiment, and from that experiment it was stated that a current carrying wire and a magnetic needle was placed near it. Magnetic needle used to deflect because there is a magnetic field around it. So we get an experimental proof, or you can say this is in support with the Oersted's experiment. Number 4 that we shall discuss is at an infinite distance also. If r goes to infinite distance also, value of magnetic field decreases, because distances cannot be very infinite. So magnetic field also decreases in that accordance. So while you are moving away from a current carrying conductor, the value of magnetic field will be very small at far off points. So you can learn this formula for doing the numericals of a straight current carrying conductors. Thank you.